Okay, everyone, welcome back for another Module 3 past paper. This one is from June 2018, and we'll be working on question 3, which was about the group 4 oxides, right? So we'll be learning about the group 4 oxides through this question. So table 2 here provides data on 2 properties of the oxides of some group 4 elements, right? So they're asking us to complete table 2 by describing the thermal stability of the oxides, right? So how do they hold up under heat is what they're asking us really in this question. So if we look at the table, we'll see that the 2 properties that they're showing us, the properties thermal stability here, and then down here we have the melting point of the dioxide in degrees C, right? So the group 4 elements can exist in 2 oxidation states, right? They can exist in the +2 oxidation state or in the +4 oxidation state. So what we have to fill in is for the carbon monoxide, right? That's the oxide of carbon in the 2+ state. And for lead oxide, right, which is the oxide of lead in the 2+ oxidation state. So in terms of thermal stability here, the carbon monoxide does not decompose on heating in the absence of air because it has a triple bond present in it, and that's fairly strong. So it won't decompose in the absence of air on heating, but it would be readily oxidized to dioxide if there was some oxygen around or any air around, right? They already gave us the info about silicon oxide, and so that's readily oxidized to the dioxide form. And then the PBO does not decompose on heating in the absence of air. So this is fairly stable, right? So in the 2+ state, the PBO is very stable and won't decompose on heating unless there's air around, right? Okay. So over here now we're looking at the +4 oxidation states. So these are the dioxides, right? For which they gave us the melting point as well. And they gave us this information that carbon dioxide is stable even at high temperatures, and we were to fill in the other 2. And so what I came up with was that the silicon dioxide is stable even at high temperatures, and that's given by the melting point that you see here, right? It's very high melting point when compared to a very low melting point for carbon dioxide, but this is stable even at high temperatures, and so is this one, the silicon dioxide, right? But once we get to PbO2, which is the lead oxide in the 4+ oxidation state, there's significant decomposition that we'll see. So we'll go from the PbO2 form to the PbO and oxygen. So that's what will happen. This will break down when we heat it, right? We'll end up getting PbO plus O2, and we'll talk a little bit more about why that's the case, right? So just a little extra note here. So carbon monoxide and carbon dioxide are gases at room temperature, while all the other ones, right? So SiO, PbO, SiO2, and PbO2, those are all solids at room temperature, right? So keep that in mind. So the oxides of carbons are gases at room temperature, and all the other oxides are solid at room temperature. So keep that in mind going forward, right? So this is how we would fill out this table for our, how many marks is that? 4 marks, right? So that's how we would do that one. So then we move on to the other question, part B of that same question, which is saying that we should account for the type of structure and bonding of the oxides of the element carbon, silicon, and lead in the +4 oxidation state that's described in table 2, right? So we're to account for the type of structure and bonding that's present in those oxides in the +4 state, and use the melting point data to kind of, help us in that response, right? So let's scroll back up to the table for a little bit, where they have the melting point of the dioxides, which are the +4 oxidation states, right? So we see here this trend, low melting point for carbon dioxide. We said it's a gas, right, at room temperature. We see a very high melting point for the silicon dioxide, and then we see an intermediate melting point for the PbO2 or the lead 4 oxide, right? So let's rationalize that a little bit now. Let's explain why that might be the case, is what they're asking us to do, right? So what we can say is that in the +4 oxidation state, right, the oxides of carbon, silicon, and lead, they exhibit different structure and bonding. And so CO2, carbon dioxide, has a simple molecular structure and it is a gas, as we said, right? And the SiO2 has a giant covalent structure and it exists as a solid. And the lead 4 oxide now, PbO2, has a mixture of giant covalent bonding and some ionic bonding there. So it's like a mixed bonding system going on in the lead 4 oxide. And as we said earlier, that also exists as a solid, right? So these structure and bonding, these varying structure and bonding patterns is all reflected in the melting point data shown above, where we see the very low melting point of CO2 that's characteristic of that simple molecular structure, right? And that can be explained by the weak forces of attraction between its molecules. And then in SiO2 and PbO2, remember now, those two melting points were higher than we saw in carbon dioxide. And particularly for SiO2, we can attribute that high melting point that we see to its giant covalent structure that's similar to diamond, right? And as we said, in lead 4 oxide, it's more of an intermediate melting point because we have a mixture of covalent and ionic bonding present there. And so in that case, it would fall in the middle, in between what we see for carbon dioxide and the silicon dioxide. But the key takeaway here is that for the silicon dioxide, that structure can be likened to diamond, right? And we know how hard diamond is and how rigid and how complex, you know, of a structure that is, a giant covalent structure that is. And silicon dioxide is like that. And that's why its melting point is the highest of all the three here in that +4 oxidation state, okay? So that's how we would account for that. And that's for 3 marks, so that's good. So then we move on to part C of that question. And in part C, they're asking us to explain the relative stabilities of the oxides of the group 4 elements, carbon, silicon, and lead, of oxidation states +2 and +4. So they want us to look at both oxidation states now and just kind of say, you know, what do we see in terms of stability for these, for the oxides of these elements, right? And so here I've kind of like summarized the trends that you would see. So over here, I have the +2 state, right, which is the lower oxidation state of the two. And in this form, we have monoxide. So we just have one oxygen, right, attached to these group 4 elements. And over here, I have the +4 state, which is a state in which we have 2 oxygens attached to the group 4 elements. And these are our dioxides, right? Okay, so let's start over here with our +2 state. Looking at this, we see that there is increased stability as we go down the group, right? So of all these 2+ oxidation states, the most stable of them will be the PbO or the lead 2 oxide, right? So this will be the most stable one. And then when we look at the +4 state now, we see that the stability increase is going up the group. And so what that means is that the PbO2 in the +4 state is going to be the least stable, whereas the carbon dioxide is going to be the most stable. So we can just summarize everything down here by saying that, you know, generally speaking, the +4 oxidation state is the most stable for carbon and silicon, right? So we see that here, while the +2 oxidation state is going to be the most stable for lead, right? So that's a general observation that we can make in terms of the relative stabilities. Now let's explain a little bit more now. So as we go down the group, which is what I'm showing here for the +2 state, right? So let's look at the +2 state again. As we go down the group, right, the stability of the oxides increase. So the PbO is the most stable in the +2 state. And that's due to the presence of what we call the inert pair effect, right? And the inert pair effect is really just a tendency for the pair of electrons that are in the s valence shell. Remember, we have electrons in the s valence shell and in the p valence shell in this particular case. Well, the ones that are in the s valence shell are closer to the nucleus and closer to the pole of the nucleus. And so those ones don't participate in bonding, right? They're just there hanging out, not doing anything. And so that makes for a more stable molecule. And that's why PBO is so stable. Because remember, as you go down the group now, you're having more shells. And so the ones that are closer to the nucleus, which would be in that S shell, right, are going to be more inert and not really amenable to like reacting, right? And so that's why PBO, so this in this +2 state, is so stable as compared to the other ones, right? Now, when we look at the +4 state now, what we're looking at here is a change in bonding that's going on, right? So you see that in the +4 state, really and truly what's happening, it has to be covalent bonding that prevails, because you're not going to be able to lose 4 electrons. That's very hard, right? That will require a high ionization energy, and that's just really hard to do. So in the +4 state, the predominant bonding that forms is a covalent bond where you're just sharing those 4 with another atom, right? And so carbon dioxide, we know, would form a pretty solid covalent bond because that's a nonmetal, and then of course another nonmetal. Silicon dioxide as well, because that has it's a metalloid, so it's closer to a nonmetal, right? Or it's in between a nonmetal and a metal, but close on the nonmetal side. So there'll be a significant amount of covalent bonding or covalent character here, and that, again, we said that's what's preferred in the +4 state. So it kind of wants to do that. So that's okay, right? But as we go down here, we encounter lead, right? Lead is a metal, right? And then you have oxygen. So that's a metal and a non-metal. It's kind of, it would more likely want to fall on the side of an ionic bonding, but that's not possible in the +4 state, right? Because it's so much energy to remove 4 electrons. And so what happens is that you'll find that these ones are more stable because they can participate in that covalent bonding that they want, whereas lead can't do that. And so it's not stable. It doesn't want to be in this +4 state, so it's not stable, right? And so what's actually more stable for it is to be in the +2 state, right? So that's all I've summarized here. I've just said that when the elements are in their +4 oxidation state, they can only form covalent bonds, whereas in the +2 state, they're expected to form ionic bonds, right? So what you'll find is that the bonding changes as you go down the group from covalent to more ionic, but that's not favorable in this +4 state. And so what we find is that the PbO2 is not stable at all, and it just wants to be in the +2 state, okay? So just to summarize, the +4 oxidation state is most stable for carbon and silicon, while the +2 oxidation state is most stable for lead. So I think for this question, as long as you explain in terms of, you summarize like what you would see in terms of stability, like we just did here, right? And you kind of touch on the inert pair effect a bit, as well as the bonding that prevails in each state, I think you should be good for these 4 marks, okay? So I know it's a lot, but definitely take some time to digest what's going on here and find a way that makes it, easiest for you to remember. So, but it's all here for you to see and to really soak in, okay? Okay, so let's move on to part D now. And they're asking us to describe the expected observations when a series of different reactions occur with the lead-4 oxide. So that's the lead in the +4 oxidation state, which, as we just said, it doesn't really want to be in that state, right? It wants to be in the +2 state, where it would be PbO. So it's going to undergo a series of reactions here, and we'll just talk about what we would expect to observe, right? So in this first case, where we're adding concentrated hydrochloric acid to the solid lead-4 oxide. So the lead-4 oxide is originally a brown solid, right? So let's just keep this in the forefront of our minds. The lead-4 oxide is originally a brown solid. When we take that brown solid and we react it with concentrated HCl, what's happening is that you know, lead oxide is amphoteric, so it has both basic and acidic characters. Let me just kind of jot that in here while we're here. So it's amphoteric, it's what we call amphoteric, right? So it has both acid and acidic and basic character, right? Acidic and basic character, right? So in this particular reaction, it's reacting with concentrated hydrochloric acid, so it's acting as a base in this case, right? So a base and an acid is gonna give you a salt and water. And in the case of the lead oxide, right? The lead oxide, remember, it doesn't want to be in the +4 state, right? It wants to be in the +2 state. That's where it's happiest. And so what happens is that it's a very good oxidizing agent. So it will oxidize the hydrochloric acid to give chlorine gas and the PbCl2, so the lead chloride salt that's in the +2 state, right? So it wants to be in the +2 state. So it's a very good oxidizing agent. It's going to oxidize the HCl while it itself gets reduced from +4 to +2. And so what we will observe is a white color solid that corresponds to the PbCl2 forming. We'll also observe a yellow gas with pungent odor, and that gas is chlorine gas, right? So again, the PbO2 doesn't want to be in this state, so it's a very good oxidizing agent, and it will oxidize the hydrochloric acid to PbCl2 and Cl2 gas, right? And of course, we'll get water because it's a base and an acid, right? All right. So in the second case now, as we go down here, we have concentrated sodium hydroxide solution that's been added to the solid lead oxide. Again, we said lead is amphoteric. It has both acidic and basic character. So if we're reacting it with a base, then in this case, it must be functioning as an acid, right? So it's functioning as an acid here, and this is our base. And we know that when we put acids and bases together, we're going to get a salt and water, right? So we get this salt here. This salt, they call it sodium plumbate. So let me just write that. They call this salt sodium plumbate. Just write that here. Plumbate, right? And so that salt that forms is a colorless soluble salt. So remember we said earlier that the lead oxide is originally a brown solid. Well, we would see that that brown color goes away and we end up with a colorless soluble salt, which would correspond to our sodium plumate forming as a result of that kind of neutralization reaction between the PbO2, which is functioning as an acid in this case, and the NaOH, which of course we know is a pretty strong base, okay? So in this case, we see a colorless soluble salt forming, which is a sodium plumate, and of course we'll get water because it's a neutralization reaction, okay? All right. So moving down now to this final reaction, or the final reaction that's taking place here, for which they want us to give an observation, is that we're going to have an aqueous solution of Fe2 plus ions, and we're going to just add that to our solid lead oxide, right? Remember now, we said lead oxide, it doesn't want to be in this particular oxidation state. It would rather be in the +2 state, right? So it would love to just get reduced, right? So it's going to function as a powerful oxidizing agent. And what it's going to do is it's going to oxidize the Fe2 plus ions to Fe3 plus, while it itself is going to get reduced, right? Because it's functioning as a powerful oxidizing agent. And we know that oxidizing agents oxidize another species, right? While they themselves get reduced. And so this is what the lead wants. The lead wants to be in this 2+ state, and that's what happens, right? And so in terms of observations now, because we have our Fe2 plus going to Fe3 plus, we'll see a color change that corresponds to this green Fe2 plus being oxidized to a reddish brown now Fe3 plus, okay? So those are the things that we would observe for these particular sequence of reactions that they've asked us about. And in this case in particular, for this final one, for part 3, what I would say is be sure that you are able to do this kind of analysis using standard electrode potentials as well, right? So you know to look at the value of standard electrode potentials to determine if a reaction is feasible or not. So would the lead, they might ask, would the lead be able to oxidize the iron, right? And you can look at the half equations and the associated cell potentials. And as we would have discussed in our section on redox equilibria, if a reaction is going to be feasible, right, that means that the overall standard cell potential is going to be a positive one, okay? Just be able to do that as well as it relates to these kinds of analyses, okay? Because that's a possibility of a question as well. And so with that, we will end here on our group 4 elements discussion, and I'll see you on the next video.